I'm going to be looking at how we solve these optimization problems using ideas of calculus. These optimization problems are going to be problems we're going to be asked to minimize or maximize something, like maybe maximize the profit for a business, or maximize the area that can be enclosed with a certain amount of fencing, or minimize the cost of producing some sort of can or box. And some general procedures to go through are listed here. I'll illustrate that with a problem at the bottom. So first, understand the problem, read the problem carefully, identify what we're being asked to find and what information is given. So down here, a farmer has 2,000 feet of fencing to enclose a rectangular area. A river can serve as one side of the area so that fencing is not needed on that side. Find the dimensions of the rectangle that result in the maximum area. So we're being asked to maximize the area, and we're told how much fencing we have. Parts 2 and 3 here, draw a diagram and introduce notation. That's sort of, those sort of go together here. So we know we have a river. We're not going to have to worry about fencing on that side. So here's maybe my river, relatively straight. And I'm going to make a rectangular pen along the side of that river. So we're going to need some notation. The variable quantity being minimized or maximized here, that could be Q. That's going to be the area for this. We're going to want to maximize the area, maximize Q. And then there are going to be other quantities in the problem. Well, the area of this rectangle area is length times width. So I could label those values here. And so maybe I'll label this as L, and then this is W, and of course this side would also have to be W. And what I've done is then I've drawn the diagram and labeled the diagram along with this notation, and then what I'm asked to do, I'm asked to maximize the area, which I can call Q, and that's going to be L times W. Now, so I've done that here in step 4. I've expressed Q in terms of the other variables introduced in the problem. So this area Q is length times width. The problem is, to use calculus, I want to take the derivative of Q to find minimum or maximum values of Q. But I have two variables. I really want Q only in terms of one variable, so that's step 5 here. So I want to find relationships between the quantities I've used in step 4. Is there a relationship between L and W? Well, there's one piece of information I haven't used yet. That's that I have 2,000 feet of fencing. And so what I know, if I take those three sides, because I don't have to put fencing along the river, if I take those three sides and add them together, well, that's going to be 1 L and 2 W's. So L plus 2 W, that has to equal to 2,000. And what I can do then is I can solve this equation here for one of the variables, either L or W. I do whichever one's easiest usually, so it looks like it's pretty easy to solve this equation for L. I'll just subtract 2W from both sides. So I get L equals 2,000 minus 2W. Now that's sort of the setup of the problem right there. To actually solve the problem then, I want to take this function Q that I'm trying to maximize. It was length times width, but I'm going to replace length with 2,000 minus 2W, and then distribute. So I get 2,000W minus 2W squared. And then I'm going to take that, and I'm going to take the derivative. So Q prime is going to be 2,000 minus, bring down the 2, 4W. So I'm going to set that equal to 0. And solve for W. Divide both sides by 4, and I get W has to be 500. Now, there could be a couple ways of verifying that that's actually a maximum value and not anything else. One thing is if I look at plugging in to Q prime, if I plug in something less than 500, like if I plug in, Q prime only has one solution, 500. So values less than 500 or greater than 500, I might have that Q prime is less than 0 or greater than 0 on either side. So if I look at Q prime of 400, for instance, that's 200 minus 1600, that's going to be positive 400. Whereas if I put in Q of 600, that's going to be negative 400. So that means it's increasing positive derivative, it's increasing at 400 and decreasing at 600. So it was increasing and then decreasing. This must be a maximum. So it's going to be a maximum at W equals 500. And then when I go to answer the question, find the dimensions of the rectangle. So my width is 500, my length is 2000 minus 2W. So that'll be 2000 minus 2 times 500, which would just be 1000. So my dimensions are 500 feet by 1000 feet. And that would be the solution to the problem.